All right, well, good afternoon, Tech Days. Here, I'm gonna not jump off there. Can we pull those doors closed? Would you mind? Right behind you there. Keep a little bit of the hallway noise out. Oh, look at that. Oh, crowd involvement already. Good afternoon, Tech Days. How is everyone so far? Good conference so far? Great. We've got a lot of material to cover today. We're talking about what's new in Windows 10 in the fall creators update, right? So what's coming up. When did we announce? Next week? If you're on the Insiders Ring, you already have it. And we're already talking about the new RS4 builds. But it's what's coming new. And what we've really been working on is how do we sort of package up a lot of the mitigations that are out there. And we kind of give it a name. We call it WDEG, which I believe stands for Windows Defender Emmet is gone. But just to kind of give a sense of where that fits onto the stack, I wanted to kind of portray what we've been building into the platform itself, and then we're going to go deep into what we now just refer to as Exploit Guard. And even it was so recently named that when I submitted the session, I didn't have a name to put on it because we just came up with that. When we look at what we're doing off of the machine, right, in Office 365 and in the browser, a lot of the work we're doing is how do we keep malicious software, malicious actors off your machine so they don't get there in the first place. Once we're actually on the machine, we're looking at how do we make it easier to lock down the devices. So things like Win10s, which will use some of the protective technologies to keep certain software from running so it just never runs in the first place. How do we control the applications that can run? Right, so that's what historically we referred to it as Device Guard, which is sort of the successor to AppLocker, although AppLocker is still relevant, as we talked about in my session yesterday. And then AppGuard, how do you isolate applications? And we'll go really deep on what it means to be Exploit Guard, how we're protecting really deeply each individual application running on Windows itself. The antivirus, which goes through and tries to detect things based on not only signatures, but also on behavior. And the ability to analyze some of the advanced behaviors based on the telemetry that Windows emits using Defender ATP, or Advanced Threat Protection, which is a service that we offer. And then how do we, off the machine, help protect your backups in the event of a really common recent threat, which is ransomware, so that the ransomware can't just overwrite your backups and make it unrecoverable. So our focus will be on the Exploit Guard, and I'm going to give a short overview of the philosophy by which we're building. We're trying to build it to real-world threats. Understand how do we minimize the attack surface, right? So in addition to principle of least privilege, the principle of least exposure. If you don't need to have something running, don't have it running. We want to understand what our adversaries are already doing and break those techniques. We want to understand how we contain the damage so we can't do as much damage. We want to limit the window of exposure that we have. So I'm going to take you on a whirlwind tour, and I only have 45 minutes, so we're going to have to keep moving pretty quickly, of the different features groups that we have in Exploit Guard. So the first one is attack surface reduction, which is really about how do we limit what an application is able to do. And the big example we see today is in Office, because if you look at how do you defend against things, even with application whitelisting, it's really hard to defend against the Office applications you may have. Because what we have today is, hey, here's all the Office files, right? Now, if you want to protect against potentially malicious code in Office files, you could just use AppLocker or Application Control, part of Device Guard, and just block access to all Office applications, and that would solve that problem. Not very good for productivity, though. So then you say, well, what's the real problem? Well, it's macros. So I could just block everything with a macro. And unfortunately, a lot of people wrote a lot of macros. So if we just block macros, that's still not enough. And you could say, well, I'll digitally sign all of my macros. Well, when people have macros, they tend to have a lot of them, and that process is really hard. So what if we instead looked at, well, what are the macros behaviorally doing that I should be concerned about? Are they executing other content? If they're executing other content, I might want to be worried. That's a signal that that's a macro that I may want to be suspicious of. Or if my macro is reaching out to the internet and downloading something, it almost certainly is something bad. So let's look at the behaviors. And what we did is we built the way to drive some rules to constrain what those Office macros are able to do. So we can start to close down that workaround, that hole that a lot of folks have, by doing things like, hey, let's stop all of your Office apps from creating executables, from spawning child processes, from having obfuscated code, from calling directly into Win32, which is how you call into the kernel, right? Let's just block those behaviors of those applications. And let's actually take a look at what that looks like so we can see it. So we're able to manage all of this through whatever management approach you're using. You can do it through group policy, you can do it through Intune, you can do it through Configuration Manager, and you can do it through PowerShell. I'm going to do it through PowerShell today. So what I'm going to do is I'm not going to enable any rules yet. I'm going to show you the example of what we're going to show. So what I'm going to do here is I'm going to create a child process. So if we kind of watch what's going on in the below window, it's going to go into WinWord, and from WinWord try to launch Notepad, and it's going to succeed. And then it's going to close it when it's done and kind of clean up after itself, just to showcase, hey, Word can launch a child process. When I put on the attack surface reduction rules, and I'll just go ahead and execute them all, turn them all on. Yes, we did put in these nice friendly GUIDs, right? That makes it super easy to configure. I don't get some of the decisions we make either, but at least they're well documented. So I'll go ahead and run all of those rules, and now they're all applied on my device. Incidentally, that configuration does require administrator privilege. So it's not something that the bad guy can go and turn off, which is something you should think about. If the bad guy can turn off the rules and then run the thing, then they're going to turn off the rules, right? So there has to be an admin to apply it. So I have this one elevated, but now when I try to run it, it's going to go this time through OneNote, and I'm blocked. Oh, it doesn't. That's an interesting zoom. I'll have to file a bug against Zoom it. But it's been blocked, right? And call your IT help desk to get that fixed. So now we've actually actively blocked that content for a behavior that we probably don't have a legitimate use case for. So that's attack surface reduction, which has, manageability points, right? So we can see that through, whatever management tool you have and are using today. You can put it in there. And note that this has already been effective against a real-world attack. And those who are on the Windows Insider program had this defense. So if you look at CVE 2017-8759, it was actually a vulnerability in the .NET framework, which has been fixed. But the vulnerability was triggered through an Office at macro, which would then tee off and start an additional process that was running the .NET framework. Well, the Office macro can't launch a child process from the .NET framework because of Defender Exploit Guard. And so you start to get this protection array. This is not a hypothetical. This is protecting against real-world threats. So let's talk about the next of the features, or sort of four main feature groups we'll talk about. And this one is called control folder access. And this is really the defense that we're putting together against ransomware, right? Because that's been a very dominant threat in the environment. Because ransomware will typically somehow find a way to get on the device and then start encrypting your file, demand a payment, and then if the victim chooses to send the money, then maybe they'll send them a decryption key. The keys behind that are they want to make sure they stay anonymous. It changes all the time. We see a lot of polymorphic malware, and it tends to be extremely damaging. So if you look at what happened in NotPetya, for example, one of our customers had 70,000 devices rendered completely useless in under a few hours. I don't name names. I'm not a name dropper. I don't kiss and tell. I also don't kiss them, so just to be clear. So what is controlled folder access aiming to do? Control folder access is all about defining what folders are we going to constrain what you can write to altogether. Because again, let's think not about the specifics of all or nothing, but about the behavior. What should be able to write to your My Documents folder? Well, applications that you've installed legitimately. What shouldn't be? Some applications sitting in your downloads folder probably shouldn't be able to write there, right? Per user install shouldn't be able to write there. It's, in essence, almost like a very miniature version of application whitelisting, except for it's not whitelisting it to run, it's whitelisting its ability to write to a particular location. So that makes it really compatible, and it's really designed to slow things down in terms of what's going on the device. So let's take a look at what that looks like. And for controlled folder access, I'll go ahead and close this guy out. I've got another tool that all it's going to do is create a file. And let's call that file TechDays17.txt, and I'll drop it on my desktop, which, of course, today I can just do. Right, so now it's created a new folder on my desktop, and hooray, that worked great. This is an application that's just sitting on my desktop. It's not in a trusted location. Now let's go through and apply our, let's disable my ASLR rules first, real quick, while we're driving past here, and enable controlled folder access. So now that I have it enabled, I'll go ahead and restart the application so it'll pick that up. And now I'm going to try to write to my desktop, and it's going to fail, because this is not sitting in a trusted location. It's going to alert me, hey, it blocked us from making changes. It's coming from a place that we don't expect and we don't trust. So it's a simple way of ratcheting up trust, because that's what you're really concerned about. You're concerned about, if you're a home user, the pictures of your family, the documents you've made. If you're a business user, you're concerned about the documents that you're generating. You can, incidentally, in addition to just enabling it for the default folders, add any additional folders that you need to, right? Here via PowerShell, but via policy as well, so that if you have, say, a default user directory on a file share, you could add that. If you put in some other folder taxonomy, you can put all those things in there. So you can completely control that through the policies to determine, hey, these are the places that only my trusted applications should be able to run. Right? So another really strong defense around what's going to be allowed to make changes on the system. The third of 4 features, network protection. Right? And this is really building upon work that we've been doing in the browser space. Right? The attack surface is this. When we look at what adversary behavior tends to be, what are people doing on our endpoint devices, is typically, most of the time, to be honest, someone's sending a phishing email and one of your users is clicking. Right? It's so effective, right? And they provide some credentials, right? Or whatever the case may be, whether they steal them. Somehow they end up with malware on the device. Now, more and more, what we're seeing is malware that does not want to stay resident on the device. You don't want to have it there and available for inspection by your antivirus systems and other heuristics. It wants to stay in memory. So a very common pattern is for that malware to reach out to a command and control server and download the actual malicious software and only have it exist in memory. So it's not sitting on the disk. It's not even coming across the network unencrypted. So oftentimes it will be lightly encrypted. A common thing is to have like a PNG file where you'll base 16 encrypt the malware inside of the PNG. So you get a little bit of fuzziness in the PNG, but they don't really care. They're not trying to show you a great picture. They're trying to get the malware through all of your defenses and then rebuild it in memory. So what we want to block is that network connection to tie that to the reputation services that we've been building, right? In essence, it's SmartScreen for all of your other browsers and all of your other processes. We already have had this in Internet Explorer and then in Edge. And, in essence, we apply it through the network filter driver. So the network filter driver is going to go about making a connection, but when it does that, it's going to call into that service that's going to retrieve information from that cloud intelligence. So the reputation service that we stood up and introduced back in Internet Explorer 9. We then, of course, cache everything because we want to limit the amount of network traffic you have in every network call. So we'll cache when you go to a known place again so that it continues to be known. And update it over time so that we can build the right level of performance with intelligence. And it ends up being really effective. When we look at our malware block rate, right, it's still really good. So this is, particularly when used with other browsers, in addition to what they're providing as well. And more importantly, I think, is that it also blocks the applications that are running, perhaps a malware unpacker that you got through some phishing mail, from reaching out to the internet, which is something we just didn't have before. So let's take a look at what that looks like. And to simplify that, what I'm going to do is I'm just going to use another browser, right? It's easier than writing malware. And this is a test that we stood up to test SmartScreen. So if I just go ahead and refresh it, it's going to be like, hey, it's a test page for SmartScreen, right? This is beautiful, rendered. Clearly, a developer wrote this. Well put together. Developers not generally the best designers. I can say that because I am one. But let's enable network protection. So with network protection enabled on the system, when I go to refresh it, actually, Try this again. Is it cached? All right, let's try clearing the cache. Boy, this is a epic demo fail. I just did this too. Where do I clear my cache on Chrome? More tools. Yeah, look at this. Yeah, clearly I'm not a... Okay, got it. All right. Let's try this again. Chrome. And now we'll go. And yeah, now we're not looking at a cache connection, right? Because we could see the alert coming through. It was like, hey, we're not letting you get there. But then it was going and pulling the cache. So we clear the cache, and it's like, hold on. We blocked it. And similarly for any other application. So it's not going to get the same nice UI. So Chrome is not going to trigger its own warning and bring up its own nice red page because we're not integrated with that. We're just blocking it at the network transport layer, so you just can't get there. So now we have the ability, as never before, to really start blocking these connections across the bar and start to block that one commonly used adversary technique. So now we can get to a much stronger use of the reputation service and the data that exists up there. So 3 big features, and you saw that they were actually really easy to go through and configure, right? The attack surface reduction, here are the options. Turn them on, turn them off. Relatively straightforward. If I look at controlled folder access, turn it on, maybe modify the folders, or turn it off. Very straightforward. Network protection, on or off. These are very straightforward. The next segment, we cover the stuff that's a little bit less straightforward, the exploit protection. And I made my, some of you gave me a courtesy laugh at the beginning, my little joke about Emmett, but that's what we really used to use for exploit protection. The reality is that we've actually exposed most of this functionality to developers for quite a long time. But not all developers were aware of what everything did or turned it on. Perhaps the application predates when the controls are put in place, so the compiler just flat out didn't support it. What Emmett allowed you to do is it allowed you to say after the fact, after it's been compiled, take existing software and add additional protections to it. Things that simply weren't supported before. Emmett, however, you may have noticed we've put an end of life on it, and it's July of next year. So you have about 6 months to use it. So if you're currently using Emmett, that's great. It's provided you with some great protection. Have a look at Exploit Guard because it replaces it, and in fact, not only replaces the functionality that was there, it adds even more functionality that I think is even better, right? Because now we have a much more controllable UI. That was actually one of the funniest bits of the conversation is when we declared that we actually got a UX designer to work on this feature. The team that builds these things had never had a UX designer before, and so there was like a little party about it because they work on grungy internal stuff and never get UX designers. What we have not yet done, however, is we've not yet gone through and said, here's what all of these switches are. So in the next 26 minutes, I'm going to try and explain these. These are individual protections that you can apply specifically to applications that are running on your systems. A lot of times, the target you'll have will be applications like web browsers and Office applications. And the reason why you would want to put on protections afterwards is not because the developer of those applications didn't know it. I assure you, the Office team and our browser team and the Chrome browser team, probably the Firefox browser team, although we're not as close to them. At least my team isn't familiar with them. We have worked with them in the past. Probably knows about all these things. Why don't they turn them on? Because they all have add-in models. And even though they may be compatible, their add-ins may not be. And so if I turn it on in the compiler and by default, and there's no means to turn it off, all of those add-ins could break. And guess what happens when you ship a version of Office that breaks someone's critical add-ins? No one puts it on. So here's what they are. We're going to kind of go through these, but I think it's interesting to think about what all of these things are. The first control is one called Arbitrary Code Guard. And what Arbitrary Code Guard does is that it prevents you from allocating memory where you've enabled the execute bit. So at what I can allocate memory, I have read, write, and execute as 3 different configuration options. Any of those that include execute, I don't allow you to allocate memory. That's a very common trick, right? Because I want to get the memory that I want on the system. So I'm going to write some malicious code on there and then start executing it. Well, data execution protection, which we'll see later, will stop me from doing that. So if I try to mark it as executable, this will say, no, you can't do that. And it does require re-architecture for some processes. For example, we had to refactor what we were doing in the Edge browser. So Edge browser has this already enabled, so you don't need to turn it on retroactively. But in the Edge browser, there are 2 things we do that generate arbitrary code. One of them is JavaScript, because JavaScript reads your script and generates machine language that has to be executed. It's generated in real time, which means we had to move it out of the Edge process and have a separate process for the Chakra engine. Similarly, the advanced rasterization platform, which lets you do some of the 3D things, had to be moved out of the Edge browser itself and into a separate process that didn't have arbitrary code guard enabled. So if you have some features that require arbitrary code guard, you may have to refactor the application in order to get that working. But if you don't have any, it's a very effective protection to stop an adversary from generating their own things. Next protection, blocking untrusted fonts. And this one's very straightforward. Fonts have a direct pathway to GDI, although we've simplified that and done a little bit of refactoring so far. It's better than it was. It used to be directly running in kernel mode, right? So it's better than it was, but there's still a path by which a font could be used as a pathway to exploitation. This just says if it's not in Wind or fonts, we're not running it. We don't load it. Nothing else works. So we can start blocking untrusted fonts. Another one is ASLR, right? And before we kind of get into the controls, I want to make sure we understand what ASLR is. Now, ASLR, here's how the protection works. If I'm the bad guy, I want to run some code. And if I do things like block arbitrary code guard from me putting in code and marking it as executable, and I compare that with something like data execution prevention, which blocks me from executing something unless it's marked as executable, those 2 pair up very nicely. If I can't get that on the system, the next thing I think about is, does the code I'd like to run already exist in one of the functions already on the system? So for example, if I want to create a file somewhere, I could call the create file API, set my instruction pointer there, and start running it, and just load up the registers with the arguments I'd like to have, and now I'm manipulating your code to do something for me. What ASLR does is it says, I'm not going to let you jump directly to that one spot in memory. I'm going to have things be in a different random place every time to block that attack vector. So now every single boot up, right, it's going to move around so that I can't just directly target it. Now the thing about ASLR is that it is enabled not only per process, but per individual binary. It has to be opted into at compile time. So what happens if you haven't opted in, but you want that protection? Because it's a really good protection. We have 2 mitigations available in Exploit Guard. One of them is mandatory ASLR. So what mandatory ASLR will do is, if you are trying to put something into a target location, so when you compile a DLL, that compilation comes with what we call the preferred base address. And if you look back all the way back to the 1990s when we were first developing Windows, or I guess it was technically the 80s, but really the 90s is when Windows came into how we did things. A DLL would have a preferred base address because every time you end up with 2 things asking for the same spot, you can't have 2 DLLs sitting in the same space in memory, so one of them has to move. And that way, now they can both be sitting in the same address space. So in order to support moving, we have to support DLL rebasing to support the ability to move. Rebasing is just to go through everywhere where you reference one address and change it by how much you moved it, right? Either add 10,000, subtract 10,000, wherever else you moved it to. It's called rebasing. Now, it takes time to rebase a DLL. So back in the 90s, we said, hey, let's not rebase. Let's compile everything so it's always in the same spot, and all of my DLLs all fit nicely and perfectly, and put in a preferred base address. It was for performance reasons. Today, we run really fast, so that's not as much of a concern. We want to be able to move them around. And so what mandatory ASLR does is it finds your preferred base address and just sticks some memory in there first. So when it tries to go there, someone else is already there, and they have to move. So it's kind of a trick, but it gets it so that it's now moved somewhere else. Now, mandatory ASLR will move it, but now we've noticed we've just changed the problem slightly. We've changed the problem from you're always at where you want to start to either you're at where you want to start or you're at where you go when you can't get there, and that turns out to be fairly predictable. So we have a second option called bottoms-up ASLR, which not only allocates some memory right where you want to go, but it allocates a random number of additional blocks at the beginning of memory between 0 and 256 64K blocks that's different every time. So now when you're moved, there's already stuff in the way of where you want to go next, and you've got to go yet somewhere different, and that can change. So it adds some randomness to where you move it around. Still better to compile it with ASLR if you can, but we can get a lot of the randomness that ASLR would provide using this approach. So I can add some additional security there. The next protection, code integrity guard, right? And what this just validates is that if I'm going to load a library, it has a valid signature and it's a valid location. So if you're loading something off of the internet, we'll block that from happening. We'll block anything that is not digitally signed. That is a trend that you will notice more and more. If your applications that you're taking in are not digitally signed, it's going to get harder and harder to apply security constraints against those. The next mitigation is control flow guard, and this one's a little bit different because I can enable whether or not it works, but it turns out I have to compile it that way. And to show why, I'm going to do a demo, right? And really, I think this is a 400 level session, right? So the way that I really think of the levels in sessions, right, is 100 should be marketing, 200 should be overview, right? 300 you should see code, 400 you should see a console mode debugger. So I've got one of those. And I'm going to show exactly what the difference is. So I have a binary, and I'll show you what the code is, right? It's using what's called an indirect call. You don't have to understand C in order to understand this. I will try my best to explain it. This is honestly the best way I've found so far to explain it. This is a function that I'm calling, and what I'm taking in as a function is a pointer to something else to call, and then it's just running whatever that function is. In essence, I don't know what routine I'm going to call. I'm going to call whatever you ask me to. So how that shows up when it's compiled into assembly language, right? And it's a quick tour of assembly language, because I understand even people who do speak a little bit of assembler probably haven't spoken it for 20 to 30 years, and that's okay. Right? Sub is subtract, right? Subtract this number from whatever this other number is, and that's the result. Call is, hey, call this function. Jump over here and do this code, and then come back to me when you're done, right? And you can see what happens when we have an indirect function call. Call whatever function is pointed to here. I don't know what it is, right? So you go find out what it is. Bad guys love that, because they'll just modify that memory to call whatever function they want. How do you stop them from doing that? So what control flow guard does is it adds, before we do that, right, there's the indirect call. Before it does that, it actually says, hey, is that an okay place to jump to? If not, don't jump there. Just crash the application. Right, which is a common approach. Like a lot of these things is if you don't work, we'll just crash the application. And then when we're compiling it, we will note in memory, hey, where are all the places that are okay to jump to? So we'll put, 1 is yes, 0 is no. So it means that lookups are very, very efficient. Right, it's O of 1. but it has to be compiled that way. We have to know yes or no. So if I enable control flow guard, but you're not compiled supporting control flow guard, it doesn't do anything. It has to be compiled, right? And I want to go into details, A, because I think it's a good control, but B, it's not a control that has a lot of adoption yet. Windows is compiled this way. Office 64-bit is compiled this way. Office 32-bit isn't, nor is anything else that I've ever found anywhere on planet Earth. And the reason why is that it increases the amount of time it takes. Now, it's an O of 1 function. So again, we'll go back to Computer Science 101. O of 1 means no matter how big the program, no matter how big the problem space, it always returns in the exact same amount of time. Problem is that amount of time changes. An indirect function call takes about 14 CPU instructions, CPU cycles, if you will. And that additional call brings that total to 40 CPU cycles. So it ends up being about a 200% performance hit on that one function. Again, it's 40 CPU instructions. And in today's processors, that's not a whole lot unless you're doing a lot of indirect calls. Right? So what I expect to happen in the developer ecosystem is for compilers to stop generating as many indirect calls where they can optimize around that when that becomes a perf problem. Right? So we don't see a ton of adoption yet, but we see some, right? And you want to know that, hey, it's going to have to be compiled that way. The next control is data execution prevention, which is one that's been around since XP Service Pack 2. And it's really useful. And in essence, what we're trying to block is this. This particular, again, here's a bit more code on the screen, that if we're putting in, hey, here's an argument, and it allows 8 characters, but I don't stop you from going longer. A classic buffer overflow. I can write whatever characters I want to, as many as I want, and we'll just keep writing it in memory and keep going until you get to done. So in this case, what we've done is we've given just a bunch of A's. So you can see the A's, we allocated 8 characters, so the first 8 A's landed there. But then we still had more input, and we didn't stop it from going, so we just kept going. And so we overwrote the variable J. 65 is the ASCII code for the character A. So we kept writing there, and we still had more A's. So we overwrote the base pointer, return, and then we got to the return address. And we overwrote that with whatever we wanted to put there. Now, what the adversaries love to do is not only overwrite with the letter A, but to overwrite it with code. Right? Because now that I've owned the return address, when I exit from the function, I'm running whatever code the adversary wanted. And if it's code they just wrote, now they're running code that they got to plant there. Data execution prevention, what that blocks is that as soon as you try to set the pointer to that memory you just wrote, it's not marked as executable. And we actually have explicit support in hardware. Right? Any Intel processor made in the past probably 15 years has this natively, and it'll generate an interrupt, and it'll crash your program. Right? Crashing your program, right? No one likes programs crashing, but which would you rather have? Your program crash or the bad guy runs whatever code they want to? I'd rather have the program crash. We can disable extension points. So over the years, Windows has added a lot of ways to add new code that can run when you run things, right? So app init DLLs, when you're initializing the application, it'll just load a couple of extra DLLs in there. That's a great persistence mechanism. It's a way for applications to hide so you don't know that they're there. This just turns these features off, right? So if you need them for compatibility reasons, if you're actually using, you can leave it on, right? But where you don't need them, it disables those extension points and blocks means by which an adversary can get persistent code running. We can block direct calls into win32k.sys, which is how I make a kernel mode call. If you don't need to directly make a kernel mode call, and you probably shouldn't, most of that should come through Win32 APIs and not your code directly, just turn it off. We can block all child processes, right? Clearly, this is not something we would want to apply globally. Imagine if we applied this to Explorer.exe. Right? That wouldn't work well. But if your application should not ever spawn a child application, this will stop it. So we saw the special case of Office apps saying, hey, macros don't spawn child processes. This will be, well, hey, my accounting app shouldn't spawn a child process. So even if it gets some code injected into it and it wants to run something else, that will be actively blocked. I can block remote images. One bit of functionality that got added to load library is load library will let you pull from a network or even pull from the internet. And we can just say, nope, if it's not local, we won't have load library bring in that DLL. Blocking low integrity images. So this requires a little bit of understanding of the integrity levels in Windows. And that was something that I explained in the previous generation of this security internals talk, where we talked about integrity levels. Really they were introduced back in Windows Vista timeframe. But in essence, it's a way of saying that something is untrusted. You can actually see it if you poke around in Process Explorer, which is a sysinternals tool that shows you details about all the processes running on a system. One of the columns that they have in here is the integrity level. Right? And so system is going to be, services that are running on the system. High are things that are running as admin. Medium are things that are running as a standard user. And low is specifically untrusted. In this case, the only ones I have running low are my app containers. If I were to, let's get Chrome running again. Chrome will run, technically we call it low in Process Explorer, but we're actually simplifying it. Chrome wanted to be clever. And if you look at what they're doing with their integrity level, it is actually, oh, wow, they actually are low. They used to be untrusted. Let's see if I'm just looking at the wrong one. Integrity, yes. Yeah, they're like, you know what? What's the lowest one we've got? 0? I'll take that one. Right? Technically, it's a 32-bit number, so there are 4 billion different possible integrity levels, right? We group them into 4, right? That's enough. But I exported XE runs it low. This Chrome, which is probably an extension is running at low. The actual primary UI is running it untrusted. And what this mitigation will do is say, hey, I'm not going to let you load in anything marked with low, which means anything that came from your web browser, anything that came from Office, because Office also runs at low if you open up a document that has mark of the web, indicating it came from the internet. Adobe Reader runs at low. So if you compromise Adobe Reader, this will block it from loading whatever Adobe Reader happened to put on the file system. So another mitigation to stop your app from taking input that you don't trust. We can do export address filtering, right? So export address filtering, in essence, allows us to figure out if you have overwritten an entry point to redirect to some other bit of code. Or similarly, import address filtering. I'll kind of talk about them together because this defines how we integrate with DLLs. Because we talked about rebasing when we talked about ASLR. DLLs can move. How do you accommodate the fact that DLLs can move? We have a table. Here's this DLL, so we'll take the kernel32.dll. It's nice and low. I can point to it here. Say kernel32, and here's this function, create file mapping W, and it sits at this point in memory. When we're loading it, we load that DLL, and if it's been moved, we'll put the actual location. So here's the base address of the DLL. We'll add on some bit of memory, right, and the offset, and get to the final thing. So we just take the base address and add the base address to the offset every single time and populate that table. So what we do with import address filtering and export address filtering is make sure that the target address exists between the start and the end of that particular bit of memory. So kernel32, we know its start, we know its end. Here's a table. We'll just validate. Hey, is this new address you put in here, is that somewhere between those two, or has someone changed it? Now, potentially could impact things because there are mechanisms that actively use this. App-compat shims, for example, modify the import address table and will redirect you to a shim DLL, right? So filtering that would cause it to break. All of your shimmed applications would fail. So you might want to take a look and see if there's anything shimmed. There are also other things that I've seen that were less friendly that will do filtering. So for example, Microsoft Detours I've seen used by a computer manufacturer that will go unnamed, that they applied it to every single process and ran some additional extra code that no one could figure out why they were doing it. And it would block that, and you'd probably be thankful because it was causing lots of things to crash in their machine. Simulating execution, right? If I'm returning from a Windows function, so it's only Windows functions because we're actually executing a check, when I do that return, I'll actually execute the next few lines and see if it looks like something's been tampered with. This is protecting the return to make sure that we're landing in a legitimate place in memory. I can validate API invocation. So if I'm calling into Windows, I want to make sure that it's a call and not a ret. Right, so someone's actively invoking it and not just returning there, because if they're returning there, that's potentially a return-oriented programming attack or a ROP attack. So it will block those things from happening. I can validate the integrity of the heap, which just adds additional protections. It puts on guard pages, it allocates things randomly, and just kind of moves things around if I'm using a memory-based attack that way. I can protect against exception handling. Here's yet another means by which an adversary could stage an attack, is that when we look at exception handling, it's a chain. I've got a bunch of functions that I may call. There may be a lot of people who are interested, right? Think of if you try catch blocks, if you're familiar with that. I think that's even in JavaScript, right? So when you catch it, there's a lot of people who may have you in a catch block, and we'll iterate through all of them until we get to the end. What structured exception handling override protection will do is it will verify that the chain actually completes at the end. We'll put a cookie there. And before we execute the exception handling, we'll run through and follow the linked list all the way to the end. And if we don't find our cookie, we'll know it's been tampered with. Now, if you're thinking, hey, I know a little bit about linked lists, what if I just took my function, stuck it in there, and then completed the linked list and pointed to the next one? Doesn't protect against that, right? But what we're trying to do is stop you from getting the code running in the first place, right? If you're just writing memory as input, you haven't written code yet. And it's fairly difficult to modify a linked list reliably in the right way without code, with nothing but data that you stamp in there. So it's still, even though it's not an imperfect one, it's still a very good protection because of the constraint the attacker has. So a structured exception overhandling. We can also validate the usage of handles to make sure that if you actually have a handle and not just some random invalid point in memory when you're making a call. Now here's one that I don't think any of you will ever have a use for. We use this in Edge, and I don't know where else you'd use it, because the idea is this. When you try to call into load library, we'll do a check and say, are you digitally signed with a Windows digital certificate? So unless you have a standalone exe that loads no DLLs ever, other than Windows itself, this will break you, and therefore is probably not that interesting. But if you do have a very simple exe that doesn't do anything but load Windows API functions in its DLLs, then that can actually block all those other things from running. And I can also validate stack integrity. So this is another means of attack, which is if I'm going to create what's called a shadow stack. Boy, that coloring makes it white on yellow is very easy to read. But it turns out there's actually not that interesting stuff up there. What you care about is there's two different things. So here's the thing. A stack is just a chunk of memory that I just keep pushing and popping from, right? Push is just throw it on the top, throw it on the top, throw it on the top, throw it on the top. Pop is, hey, go fetch what's on the top and push it down to the next one. So you just keep adding stuff. It's just a chunk of memory. Right? We treat it differently because it has a specific functioning use, but in the end, it's just memory that goes up and down and I move things. Well, what an adversary will often do is just create a second one where they'll replace something on there. So if they want to get a whole different chain of execution, they can build a stack that will actually go through and from the return process, just keep chucking it over to new bits of code that I want to run in the order I want to run them with the arguments that I want. And now the only thing I have to get modified is, number one, write the new shadow stack. Number two, be able to modify the stack pointer, right, which in 32-bit Windows is the ESP pointer. Modify that to point at my shadow stack. And now I'm running whatever code I want in the order that I want to. So what validate stack integrity will do is when you enter into a Windows function, right? Because again, since we're running code, it has to be inside of Windows, right? So you enter a critical Windows function, we'll just do a quick check. Hey, is the stack pointer actually on a valid stack, or is it just pointing at some random little chunk of memory? And if it's not on a valid stack that's been allocated for the application, we'll chuck it out, not execute the code, and be done with it. So that, boy, that was a whirlwind tour, wasn't it? That's what all those things are. We never really explained them. That's why I wanted to take the time to say, here's what these things do. The net takeaway, because I know that there are probably a few OS nerds in the audience who are like, yeah, all right, I get some of these things now. Right? There's probably a few people who are sitting there going, what the hell just happened? Right? For those of you, and that's okay, right? Because we were in a console mode debugger, for God's sake, right? That's okay, right? The thing is that this is defending against the mechanisms that adversaries are actively using. And you can apply it to the programs you want to without having to recompile them. And that's important because the average age of an enterprise application today, average, is 12 years. That means half of it's older. 50% of all enterprise code running today is Visual Basic 6 or earlier. We have a lot of stuff that we need to protect. We have the best toolkit we've ever had for protecting it without just going and recompiling it all. And that is a big deal. So hopefully you took something away. You'll go home and try it out, at least some of the on-off features, if not digging deep in the application exploit protections. Thank you very much for coming, and enjoy the rest of the show.